Carbon compounds. What is compound? The compound is a substance made of two or more elements in a fixed ratio. An element is a substance made up of atoms. An atom is the smallest unit of element. What are the types of compounds? Organic and inorganic compounds are two main types of compounds. Objects in everyday use such as foodstuff, fibers, paper, medicine, wood, fuels are made of various compounds. Which constituent elements are common in these compounds? Except for the materials fabricated from glass and metals, all other materials are made of organic compounds. The essential element in all the organic compounds is carbon. The compounds carbon dioxide, carbon monoxide, carbide salts, carbonate salts and bicarbonate salts are exception. They are inorganic compounds of carbon. Bonds in carbon compounds. We have learned about the ionic compounds in the previous chapter. Ionic compounds have high melting and boiling points and they conduct electricity in the molten and dissolved state. Generally, most of the carbon compounds are found to be bad conductors of electricity. From it we understand that structures of most of the carbon compounds lack ionic bonds. It means that the chemical bonds in carbon compounds do not produce ions. The driving force behind the formation of bond by an atom is to attain the stable electronic configuration of the nearby noble gas and obtain stability. As the valence shell of carbon contains 4 electrons, there can be many alternative routes to attain a noble gas configuration. To attain the configuration of noble gas, helium, He, by losing one after another all the 4 valence electrons. In this method, the net positive charge on the carbon atom goes on increasing during loss of every electrons. Therefore, to lose the next electron, more energy is required. Moreover, the C4 plus cation that would ultimately form become unstable because it has a small size with high net charge. Therefore, carbon atoms does not take this route to attain a noble gas configuration. To attain the stable configuration of the noble gas neon, Ne, by accepting one by one as the 4 electrons in the valence shell. In this method, the net negative charge on the carbon atom goes on increasing while accepting every new electron. Therefore, more energy is required for accepting the next electron by overcoming the increasing repulsive force, making the task more and more difficult. Moreover, the C4 minus anion ultimately formed would be unstable as it would have a small size with high net charge, making it difficult for the nuclear charge plus 6 to hold 10 electrons around it. Therefore, carbon atom does not take this route to attain a noble gas configuration. To attain the configuration of neon by sharing 4 electrons of valence shell with 4 valence electrons of other atoms. In this method, 2 atoms share valence electrons with each other. Valence shells of both the atoms overlap and accommodate the shared electrons. As a result, both the atoms attain a noble gas configuration without generating any net charge in them, which means that atoms remain electrically neutral. Due to these factors, atoms attain stability. Therefore, carbon atom adopts this route to attain a noble gas configuration. The chemical bond formed by sharing of 2 valence electrons between the 2 atoms is called covalent bond. A covalent bond is represented clearly by drawing an electron dot structure. In this method, a circle is drawn around the atomic symbol and each of the valence electrons is indicated by a dot or a cross. The covalent bond formed between the atoms is indicated by showing the circles around the atomic symbols crossing each other. The shared electrons are shown in the overlapping regions of the two circles by dot or cross. The electron dot structure is also drawn without showing the circle. One pair of shared electrons constitutes one covalent bond. A covalent bond is also represented by a small line joining the symbols of the two atoms. Let us first look at the hydrogen molecule, which is the simplest example of a molecule formed by covalent bonding. You have already learned that the atomic number of hydrogen being 1, its atom contains one electron in K shell. It requires one more electron to complete the K shell and attain the configuration of helium, He. To meet this requirement, two hydrogen atoms share their electrons with each other to form H2 molecule. One covalent bond, that is a single bond, is formed between two hydrogen atoms by sharing of two electrons. The O2 molecule is formed by chemical combination of two oxygen atoms. An N2 molecule is formed by chemical combination of two nitrogen atoms. On drawing the electron dot structures of these two molecules, it becomes clear that the two oxygen atoms in O2 molecule are joined with each other by two covalent bonds, that is, a double bond, while the two nitrogen atoms in the N2 molecule are joined with each other by three covalent bonds, that is, a triple bond. Now let us consider a carbon compound, methane CH4. You have learned about the occurrence, properties and uses of methane molecule in the previous standard. Just now we saw that carbon atom forms four covalent bonds using the four valence electrons and attain the configuration of the nearby noble gas neon, Ne, and obtains stability. This is line structure and also the electron dot structure of methane. Carbon, a versatile element. The entire living kingdom is made from carbon. Our body is also made from carbon. The molecular masses of carbon compounds range up to 10 raised to 12. This means that carbon atoms come together in a large number to form extremely big molecules. Characteristics of carbon. 1. Catenation power. Carbon has a unique ability to form strong covalent bonds with other carbon atoms. This results in formation of big molecules. This property of carbon is called catenation power. The carbon compounds contain open chains or closed chains of carbon atoms. An open chain can be a straight chain or a branch chain. A closed chain is a ring structure. The covalent bond between two carbon atoms is strong and therefore stable. 2. Two carbon atoms can be bonded together by 1, 2 or 3 covalent bonds. These are called single bond, double bond and triple bond respectively. Due to the ability of carbon atoms to form multiple bonds as well as single bonds, the number of carbon compounds increases. For example, there are 3 compounds, namely ethane, CH3 single bond CH3, ethene, CH2 double bond CH2 and ethyne, CH triple bond CH, which contain 2 carbon atoms. 3. Being tetravalent, one carbon atom can form bonds with 4 other atoms. These compounds possess different properties as per the atoms to which carbon is bonded. For example, 5 different compounds are formed using one carbon atom and 2 monovalent elements, hydrogen and chlorine, CH4, CH3Cl, CH2Cl2, CHCl3, CCl4. Similarly, carbon atoms form covalent bonds with atoms of elements like O, N, S, halogen and P to form different types of carbon compounds in large number. 4. Carbon has one more characteristic which is responsible for large number of carbon compounds. It is isomerism. Hydrocarbons, saturated and unsaturated. The compounds which contain carbon and hydrogen as the only two elements are called hydrocarbons. Hydrocarbons are the simplest and the fundamental organic compounds. Saturated hydrocarbons. The smallest hydrocarbon is methane, CH4, formed by combination of one carbon atom and 4 hydrogen atoms. Ethane is one more hydrocarbon. Its molecular formula is C2H6. Let us together write the structure of ethane. Ethane, molecular formula C2H6. Step 1. Join the 2 carbon atoms with single bonds C, single bond C. Step 2. Use the 6 hydrogen atoms in the molecular formula for filling the tetravalency of both the carbon atoms. From the structural formula of ethane and propane, it is seen that the valencies of all the atoms are satisfied by the single bonds. Such compounds are called saturated compounds. Ethane and propane are saturated hydrocarbons. Saturated hydrocarbons are also called alkanes. Unsaturated hydrocarbons. There are 2 more hydrocarbons that contain 2 carbon atoms, namely ethene, C2H4, and ethine, C2H2. Let us see the method to draw the structural formula of ethene, C2H4. Step 1. Join the 2 carbon atoms with single bond C, single bond C. Step 2. Use the 4 hydrogen atoms in the molecular formula for satisfying tetravalency of both the carbon atoms. Step 3. Satisfy the tetravalency of the 2 carbon atoms by drawing a double bond in place of the single bond between them. The carbon compounds having a double bond or triple bond between 2 carbon atoms are called unsaturated compounds. Ethene and ethine are unsaturated hydrocarbons. The unsaturated hydrocarbons containing a carbon-carbon double bond are called alkenes. The unsaturated hydrocarbons whose structures contain a carbon-carbon triple bond are called alkynes. Generally, the unsaturated compounds are more reactive than the saturated compounds. Straight chains, branch chains, and rings of carbon atoms. From the structural formulae of methane, ethane, and propane, it is seen that the carbon atom lies in the core of the molecule, while the hydrogen atoms bonded to each of the carbon atoms are on the periphery of the molecule. The mutually bonded carbon atoms in the core are like the skeleton of the molecule. The carbon skeleton determines the shape of the molecule of a carbon compound. Let us pay attention to the carbon chain in butane. The 4 carbon atoms can be joined to form a carbon chain in yet another way. The molecular formula of both these structural formulae are the same, which is C4H10. These are 2 different compounds as their structural formulae are different. The phenomenon in which compounds having different structural formulae have the same molecular formula is called structural isomerism. The number of carbon compounds increases further due to the isomerism observed in carbon compounds. The carbon chain 1A is a straight chain of carbon atoms, whereas the carbon chain 2 is a branch chain of carbon atoms. Apart from the straight chains and branch chains, closed chains of carbon atoms are present in some carbon compounds, wherein rings of carbon atoms form. For example, the molecular formula of cyclohexane is C6H12 and its structural formula contains a ring of 6 carbon atoms. All types of carbon compounds, whether straight chain, branch chain, or cyclic, can be saturated or unsaturated. Straight chain hydrocarbons. Saturated hydrocarbons, propane, C3H8, unsaturated hydrocarbons, propene, C3H6, propyne C3H4. Branch chain hydrocarbons, saturated hydrocarbons. Isobutane C4H10. Unsaturated hydrocarbons, isobutylene C4H8. Cyclic hydrocarbons, saturated hydrocarbons. Cyclohexane C6H12. Unsaturated hydrocarbons, cyclohexene C6H10. Benzene C6H6. Benzene, that is a cyclic unsaturated hydrocarbon. There are 3 alternate double bonds in the 6-membered ring structure of benzene. Compounds showing such characteristic unit structure are called as aromatic compounds. Functional groups in carbon compounds. Other than hydrogen, many more elements such as halogens, oxygen, nitrogen, sulfur, etc. can form carbon compounds. The atoms of these elements substitute one or more hydrogen in the hydrocarbon chain itself, and thereby the tetravalency of carbon is satisfied. The atom of the element which is substitute for hydrogen is referred to as a heteroatom. Sometimes heteroatoms are not alone but exist in the form of certain groups of atoms. Let us take an example of heteroatom oxygen. In alcohol, oxygen is present along with hydrogen. Similarly, oxygen is present along with hydrogen and carbon forming a group. This group is referred to as aldehyde. These compounds acquire specific chemical properties. Heteroatoms, or the groups of atoms containing heteroatoms, are called functional groups. Following are few examples of functional groups in carbon compounds. Refer image. Some functional groups in carbon compounds. Here, the free valency of the functional group is indicated by a short line. The functional group is attached to the carbon chain through this valency by replacing one hydrogen atom or atoms. Homologous series. When carbon atoms are joined together, chains of different lengths are formed. Also, when hydrogen atoms are replaced by functional groups, large number of compounds are formed having same functional groups but different length of carbon compound chain. For example, many compounds such as CH3OH, CH3CH2OH, CH3CH2, CH2OH contains alcohol minus OH as a functional group, but length of carbon chain is different. Though the length of the carbon chains in them is different, their chemical properties are very much similar due to the presence of the same functional group in them. The series of compounds formed by joining the same functional group in the place of a particular hydrogen atom on the chains having sequentially increasing length is called homologous series. For example, homologous series of alcohols, homologous series of carboxylic acids, homologous series of aldehydes, etc. A. Homologous series of alkanes. Let's count and write how many carbon atoms are present in following alkanes. Methane, molecular formula CH4, structural formula CH4. So number of carbon atoms will be 1, number of CH2 units 1. Boiling point is minus 162. Ethane, molecular formula C2H6. Structural formula CH3CH3. So, number of carbon atoms will be 1, 2. So, 2. Number of CH2 units 2. Boiling point is minus 88.5. Propane, molecular formula C3H8. Structural formula CH3CH2CH3. So, number of carbon atoms will be 1, 2, 3. So, 3. Number of CH2 units 3. Boiling point is minus 42. Butane, molecular formula C4H10. Structural formula CH3, CH2, CH2, CH3. So number of carbon atoms will be 1, 2, 3, 4. So 4. Number of CH2 units 4. Boiling point is 0. B. Homologous series of alcohols. Methanol, molecular formula CH4O. Structural formula CH3OH. So number of carbon atoms will be 1. Number of CH2 units 1. Boiling point is 63. Ethanol, molecular formula C2H6O. Structural formula CH3CH2OH. So number of carbon atoms will be 1, 2. So 2. Number of CH2 units 2. Boiling point is 78. Propanol, molecular formula C3H8O. Structural formula CH3CH2CH2OH. So number of carbon atoms will be 1, 2, 3. So 3. Number of CH2 units 3. Boiling point is 97. Similarly, butanol with molecular formula C4H10O has 4 carbon atoms. Number of CH2 units 4. Boiling point is 118. C. Homologous series of alkenes. Ethene, molecular formula C2H4. Structural formula CH3CH2. So number of carbon atoms will be 1, 2. So 2. Number of CH2 units 0. Boiling point is -102. Propene, molecular formula C3H6. Structural formula CH3 single bond CH double bond CH2. So number of carbon atoms will be 1, 2, 3. So 3. Number of CH2 units will be 1. Boiling point is -48. 1 butene, molecular formula C4H8. Structural formula CH3, CH2, CH, CH2. So number of carbon atoms will be 1, 2, 3, 4. So 4. So number of CH2 units will be 1, 2. So 2. Boiling point is -6.5. Similarly, 2 butene with molecular formula C5H10. Structural formula CH3, CH2, CH2CH, CH2 has 5 carbon atoms. Number of CH2 units 3. Boiling point is 30. What we have learned from these tables? 1. While going from one member to the next in a homologous series, A. 1-methylene CH2 unit gets added. B. Molecular mass increases by 14 units. C. Number of carbon atoms increases by 1. 2. Chemical properties of members of a homologous series show similarity. 3. All the members of a homologous series can be represented by the same general molecular formula for members of homologous series. Molecular formula of alkanes can be represented as CnH2n plus 2. If we take n is equal to 1, then we will get C1H1 into 2 plus 2. So molecular formula will be CH4. CH4 is the first member of alkane series. Molecular formula of alkenes can be represented as CnH2n. If we put n is equal to 2, then we will get C2H2 into 2. So molecular formula will be C2H4. C2H4 is the first member of alkene series. Molecular formula of alkynes can be represented as CnH2n minus 2. If we take n is equal to 2, then we will get C2H2 into 2 minus 2. So molecular formula will be C2H2. C2H2 is the first member of alkyne series. Nomenclature systems of carbon compounds. Initially, when less carbon compounds were known, they were named randomly. For example, methane, ethane. But after a certain period of time, when more carbon compounds generated, they were named according to the number of carbon atoms present on them. For example, pentene has 5 carbon atoms. C4H10, butane, can also be written as N-butane, that is normal butane, and I-butane, that is isobutane, depending upon their straight and branched chain structure. IUPAC nomenclature system. International Union for Pure and Applied Chemistry, IUPAC, put forth a nomenclature system based on the structure of the compounds. IUPAC nomenclature system provided unique name to all carbon compounds. Let's see how some straight chain compounds containing one functional group are given IUPAC names. There are 3 units in the IUPAC name of any carbon compound: parent, suffix, and prefix. The steps in the IUPAC nomenclature of straight chain compounds are as follows. Step 1. Draw the structural formula of the straight chain compound and count the number of carbon atoms in it. The alkane with the same number of carbon atoms is the parent alkane of the concerned compound. Write the name of this alkane, for example, CH3, CH2, CH3, propane. If carbon chain contains a double bond, change the ending of the parent name from ANE, ane, to ENE, ene. If carbon chain contains a triple bond, change the ending of the parent name from ane to ine. For example, if we replace double bond by triple bond and balance the hydrogen atoms, propene will be propyne. Step 2. If the structural formula contains a functional group, replace the last letter E from the parent name by the condensed name of the functional group as the suffix. For example, in ethane, CH3, CH2, if we add OH, alcohol group, E will be replaced by OL and it will be called as ethanol. Step 3. Number of carbon atoms in the carbon chain from one end to the other. Assign the number 1 to carbon in the functional group CHO or COOH if present, otherwise the chain can be numbered in 2 directions. Accept that numbering which gives smaller number to the carbon carrying the functional group. Both the numberings are equivalent, so the compound will be named as propan 2OL. In the final name, a digit number and a character letter should be separated by a small horizontal line. Chemical properties of carbon compounds. 1. Combustion. Carbon in the presence of oxygen undergoes combustion to emit heat and light. Hydrocarbons as well as most of the carbon compounds undergoes combustion in presence of oxygen to emit heat and light and form carbon dioxide and water as the common products. Apparatus, Bunsen burner, copper gauze, metal plate, etc. Chemicals, ethanol, naphthalene. Place 1 or 2 drops of ethanol on a clean copper gauze at a room temperature. Hold it on a blue flame of the Bunsen burner. Hold the metal plate on the flame when the substance is undergoing combustion. Now observe. Now place pinch of naphthalene ball powder on a clean copper gauze at room temperature. Hold it on a blue flame of the Bunsen burner. Hold the metal plate on the flame when the substance is undergoing combustion. Now observe. In the above activity, ethanol is a saturated carbon compound, while naphthalene is an unsaturated compound. Generally, saturated carbon compounds burn with a clean blue flame, while unsaturated carbon compounds burn with a yellow flame and release black smoke. It is this black smoke due to which a deposit of black soot got collected on the metal plate. This indicates that the proportion of carbon is larger in unsaturated compounds than in saturated compounds. 2. Oxidation. Carbon compounds start burning by combining easily with oxygen in the air when ignited in air. In this process of combustion, all the chemical bonds in the molecule of the carbon compound break and CO2 and H2O are formed as the products. Substances that give oxygen to other substances are called oxidants or oxidizing agents. Potassium permanganate or potassium dichromate are commonly used as oxidizing agents. Let's try an experiment. Apparatus, test tube, Bunsen burner, measuring cylinder, dropper, test tube holder, etc. Chemicals, ethanol, dilute solution of sodium carbonate, dilute solution of potassium permanganate. Procedure. Take 2 to 3 ml ethanol in a test tube. Add 5 ml sodium carbonate solution to it and warm the mixture by holding the test tube on the burner for a while. Do drop-wise addition of a dilute solution of potassium permanganate to this warm mixture with stirring. Initially, on adding the pink-colored solution of potassium permanganate to ethanol, the pink color disappears. This is because potassium permanganate is used up in the oxidation reaction. At a certain point of the addition, oxidation of all the quantity of ethanol in the test tube is complete. If the addition of potassium permanganate is continued beyond this point, it is not used up and becomes excess. The pink color of this excess potassium permanganate does not vanish but stays as it is. Addition reaction. Apparatus, test tubes, droppers, test tube stand, etc. Chemicals, bromine, water, liquefied vanaspati ghee, various vegetable oils. Take 4 ml oil of different oils and vanaspati ghee in a test tubes and add 4 drops of tincture iodine or bromine water in it. Shake the test tube. In the above activity, the observation of the disappearing color of bromine indicates that bromine is used up. The color of bromine disappears in the reaction between an oil and iodine. However, there is no change with vanaspati ghee. This means that bromine has undergone a reaction with the concerned substance. This reaction is an addition reaction. This reaction is used as a test for detection of a multiple bond in a carbon compound. As unsaturated compounds contain multiple bonds, they undergo addition reaction to form a saturated compound as the product. However, it is necessary to use a catalyst like platinum or nickel for this reaction. This reaction is used for hydrogenation of vegetable oils in presence of nickel catalyst. The molecules of vegetable oil contain long and unsaturated carbon chains. Hydrogenation transforms them into saturated chains and thereby vanaspati ghee is formed. Substitution reaction. As the single bonds CH and CC are very strong, the saturated hydrocarbons are not reactive. However, saturated hydrocarbons in presence of sunlight react rapidly with chlorine. In this reaction, chlorine atoms replace one by one all the hydrogen atoms in the saturated hydrocarbons. The reaction in which the place of one type of atom or group in a reactant is taken by another atom or group of atoms is called substitution reaction. Important carbon compounds: ethanol and ethanoic acid. 1. Ethanol. At room temperature, colorless ethanol is a liquid. Boiling point 78 degrees Celsius. Ethanol is called alcohol or spirit. Solubility, soluble in water. pH, aqueous solution is neutral. Effects on consumption, it adversely affects the physiological processes and the central nervous system. Consumption of even a small quantity of pure ethanol can be lethal. Ethanol being good solvent, it is used in medicine such as in cough mixture and also in many tonics. Chemical properties of ethanol, the functional group OH, alcohol plays an important role in the reactions of ethanol. 1. Reaction with sodium. Let's try an experiment. Apparatus, big test tube, delivery tube fitted in a rubber cork, knife, candle, etc. Chemicals, sodium metal, ethanol, magnesium ribbon, etc. Procedure. Take 10 ml ethanol in a big test tube. Cut sodium metal into 2 to 3 pieces of a cereal grain size. Put the sodium pieces into the ethanol in the test tube and fix the gas delivery tube to the test tube. Take a burning candle near the outlet of the gas delivery tube and observe. 2. Which is the combustible gas coming out of the gas delivery tube? Moderately reactive metal such as magnesium reacts with strong acid to liberate hydrogen gas. 2. Why do the sodium pieces appear to dance on the surface of ethanol? Sodium being highly reactive metal, it reacts with the neutral functional group OH of ethanol. Dehydration reaction. When ethanol is heated at the temperature 170 degrees Celsius with excess amount of concentrated sulfuric acid, one molecule of water is removed from its molecule to form ethene, an unsaturated compound. Ethanoic acid. Ethanoic acid is colorless liquid. Boiling point 118 degrees Celsius. Melting point. Ethanoic acid is commonly known as acetic acid. pH, aqueous solution is acidic. Vinegar, which is used as preservative in pickles, is a 5 to 8% aqueous solution of acetic acid. Activity. Apparatus, glazed tile, glass rods, pH paper, blue litmus paper. Chemicals, dilute ethanoic acid, dilute hydrochloric acid. Procedure. Place 2 strips of blue litmus paper on a glazed tile. Put 1 drop of dilute hydrochloric acid on one strip with the help of a glass rod. Put 1 drop dilute ethanoic acid with the help of another glass rod on the other strip. Note the color change taking place in the litmus strip. Repeat the same procedure using strips of pH paper. Note all the observation. Substance, ethanoic acid, color change seen on the blue litmus paper turns red. Corresponding pH, strongly acidic. Substance, hydrochloric acid, color change seen on the blue litmus paper turns red. Corresponding pH, strongly acidic. Substance, ethanoic acid, color change seen on the pH paper turns red. Corresponding pH, strongly acidic. Substance, hydrochloric acid, color change seen on the pH paper turns red. Corresponding pH, strongly acidic. Chemical properties of ethanoic acid. Ethanoic acid contains carboxylic acid as its functional group, which is responsible for the chemical reaction. 1. Reaction with base. A. Reaction with strong base. Ethanoic acid gives neutralization reaction with a strong base sodium hydroxide to form a sodium ethanoate, salt and water. Reaction with carbonate and bicarbonate. Apparatus, big test tube, small test tube, bent gas delivery tube, rubber cork, thistle funnel, stand, etc. Procedure, place sodium carbonate powder in the big test tube. Pour 10 ml acetic acid through the thistle funnel. Observe the changes taking place in the two test tubes. The CO2 gas of the effervescence passes through the gas delivery tube and reacts with the lime water in the small test tube. Lime water turning milky is the test of carbon dioxide gas. If sodium bicarbonate is used instead of sodium carbonate in the above activity, similar observation is obtained. In this activity, ethanoic acid reacts with the sodium carbonate to form a salt named sodium ethanoate, water and carbon dioxide gas. 2CH3COOH AQ plus Na2CO3 G CH3COONA AQ plus H2O I plus CO2 G. 2. Esterification reaction. Substances having ester as the functional group are formed by reaction between a carboxylic acid and an alcohol. Apparatus, test tube, beakers, burner, etc. Chemicals, glacial ethanoic acid, ethanol concentrated sulfuric acid, etc. Procedure. Take 1 ml ethanol and 1 ml glacial ethanoic acid in a test tube. Add a few drops of concentrated sulfuric acid in it. Keep this test tube in the beaker containing hot water. Hot water bath for 5 minutes. Then take 20 to 30 ml water in another beaker and pour the above reaction mixture in it and smell it. Ethanoic acid reacts with ethanol in presence of an acid, catalyst, and ester, ethyl ethanoate is formed. Saponification. Esters have sweet odor. Majority of fruits owe their odor to a particular ester present in them. Esters are used for making fragrances and flavoring agents. When an ester is reacted with the alkali sodium hydroxide, the corresponding alcohol and carboxylic acid in the form of its sodium salt are obtained back. This reaction is called saponification reaction as it is used for preparation of soap from fats. Macromolecules and polymers. Macromolecules. The number of known carbon compounds is as large as about 10 million and the range of their molecular masses is as large as 10 raised to 1 to 10 raised to 12. The number of constituent atoms is very large for the molecules with high molecular mass. The giant carbon molecules formed from hundreds of thousands of atoms are called macromolecules. They are from the type of compounds called polymers. Natural macromolecules. Natural macromolecules such as polysaccharides, proteins and nucleic acids are the supporting pillars of the living world. We get food, clothing and shelter from polysaccharides, namely starch and cellulose. Proteins constitute a large part of the bodies of animals and also are responsible for their movement and various physiological processes. Nucleic acids control the heredity at molecular level. Rubber is another type of natural macromolecule. Man-made macromolecules. Macromolecules were produced for the first time in the laboratory and factory with an intention to invent an alternative for rubber and silk. Man-made fibers which have strength along the length similar to natural fibers like cotton, elastomers which have the elastic property of rubber, plastics from which innumerable types of articles are made are all examples of man-made macromolecules. The structure of natural and man-made macromolecules is formed by joining several small units in a regular manner. Polymers. A macromolecule formed by regular repetition of a small unit is called polymer. The small unit that repeats regularly to form a polymer is called monomer. The reaction by which monomer molecules are converted into a polymer is called polymerization. One important method of polymerization is to make a polymer by joining alkene-type monomers. The polymers in the above examples are formed by repetition of single monomer. These are called homopolymers. The other type of polymers is formed from two or more monomers. They are called copolymers. Following are examples of man-made polymers and their uses. Polythene is formed by monomer ethylene and it is used for making carry bags. Polyvinyl chloride, PVC, is formed by monomer vinyl chloride and it is used for making PVC pipes, doormats, tubes and bags in hospital kits. Example of natural polymers are: polysaccharide is a polymer obtained from monomer glucose and occurs in the form of starch. DNA is a polymer obtained from monomer nucleotide and occurs in the chromosomes of plants and animals.